All right. So let me move to here. Because we started on Monday talking about thermochemistry, and we talked about energy. One second. All right, so we talked about energy having um, two components, right? Potential energy and kinetic energy. We talked about uh, we didn't talk about the internal energy in specific terms. So some of the terms that we're going to use today, they are the same thing that we talked about on Monday, but they got the terminology is a little bit different. So the internal energy, that's the same as the what we call thermal energy on Monday. Same thing. Uh, right? That's the thermal energy that we talked about based on the particles that make up a sample and how they're moving and whether they're moving fast or moving slow or whatever. And then we talked about thermochemistry, which is the study of heat that's either being released by a reaction or absorbed by a reaction. And so what we're going to do is talk about today another area of thermochemistry, which is the area of thermodynamics. It sounds like a really tech, and it is a, in all honesty, it's a very deep area. But for the scope of this class, we're just going to give you um, like an overview of it, because you're going to see this again in part two. You're going to see it again organic. So, but thermodynamics is the study of the transformation, right, of energy, and this happens when atoms and molecules start moving around and they start reacting with each other and bonding with each other or breaking away from each other. And one of the ways you study that is to study what we call is to study what we call the energy diagram or the reaction profile. So with thermodynamics, let me just give you an example here. So let's say we have a reactant A going to B. So A is the reactants, B is the products. When A gets converted into B, right? Something happens. Something happens to A and it's being transformed into B. So A as matter, as a substance, has a specific type of energy associated with it. And when it's getting converted into B, that energy changes forms. It changes from the energy that's associated with A to the energy that's associated with B. And so the way we kind of profile that is by using what we call a reaction energy diagram. And so the reaction energy diagram is basically a profile of the reaction. So you have an x-axis and a y-axis. On the y-axis, you have time, or what we call the reaction coordinate. On the x-axis, I'm sorry, no, x-axis you have time, y-axis you have energy. And for any given reaction, the curve for that reaction when it takes place is going to fit one of two profiles. right? It's either going to look like this, right? Well, this is A and this is B, and the energy it takes to convert A into B and all of that good stuff is illustrated here. Or that curve is going to look like this. Right? So let's talk about this curve and what it means. Right? So we know that A is the reactants, B is the product, right? And there's a gap between A and this peak right here, or the highest energy peak on the graph, right? That gap is what we call delta G double dagger. It's the activation energy. That activation energy is the required energy to get from A to here, which we call the transition state. Right, in that transition state, this is where the transformation is happening. Well, it's happening, get into the transition state too, but this is the point where the reaction reaches kind of a crescendo, right? Where you have all these partially broken and partially formed bonds, and your products, your reactants start looking more like the products and less like the reactants, and so on and so forth. So in the transition state, you have, this is your highest energy point. It's also the place where bonds are broken and formed. Right, and everything in the transition state is either partially formed or partially broken. Right, so then the activation energy is the necessary energy to get to that point. Every reaction has that. The activation energy actually dictates how fast or how slow the reaction is. It dictates the rate of the reaction. When you'll learn more about rates in part 2, but the activation energy is what dictates the rate of the reaction. So how does this tie into what we've been talking about with heat, energy, and all this stuff? Well, there's a gap also between A and B. Look right here, that's A, that's B. There's a gap here, right, between A and B. That gap in energy is what we call delta G, not without the double dagger. There's a difference, which is the Gibbs free energy. So the Gibbs free energy is the gap between A and B. And it also gives us another value, which is delta H, which we'll be talking about today, which is the enthalpy. Let me move this over. That's going to happen. So the enthalpy is the heat of the reaction, how much heat got absorbed or how much got released. So let me give you that definition down here. Right, so how much heat gets absorbed or released, that's that gap between the reactants and the products. And if you notice here, the products are lower in energy. If energy is increasing, right? If energy is increasing in this direction, right, you'll notice that B is lower in energy than A. So this type of reaction is what we call exothermic. And we're going to come back to this a little bit later. But this is exothermic. What that means simply is that energy is released. Right? The other curve we'll talk about in a little bit. But that curve is representative of you can see here, the reactance energy is lower than the product energy. In this case, if energy is increasing in that direction. Right? And so this is what we call an endothermic reaction. All right. So with that being said, let's talk about how all this stuff ties together, how delta H and not really going to talk about delta G today, but we're going to talk about delta H, excuse me, with respect to the products and the reactants and how much energy is released or how much energy is absorbed and whether or not the reaction is exothermic or endothermic. So we're going to talk about, I need to give you some kind of background, like an overview a little bit about systems and surroundings, and we'll talk about that briefly, and then we're going to move into some of the more pertinent information regarding delta H and ways to change the energy of a system, right? So now you have here some terms in terms of the surroundings and the system, surroundings and system. So the surroundings are that's everything else that's outside the system. The system is what we want to study. It may be a reaction in a flask. It may be something else, but most of the time for chemistry, it's some type of reaction that we're running in a flask, and we want to know like what's going on with that reaction. So for systems, there are three types. There's an open system, and an open system can exchange both matter and energy with the surroundings. So for an open system, you can add more matter to it. If it's a reaction, you can add more reactants to it. You can add more energy to it. You can also release energy from this open system to the surroundings and vice versa. Or you can remove matter from it. So you can exchange matter and energy. With a closed system, that's different. Closed system is like the light bulb. It can it can exchange energy with the surroundings, but the surroundings cannot exchange matter or energy with it. So only energy exchange happens with a closed system. And you can understand that with a light bulb, because when you turn the light bulb on, you can feel the heat being transmitted from it, but it doesn't absorb energy from the surroundings. In this case, being the room where you turn the light on, it doesn't absorb it. It's a sealed up system. So it's closed, so nothing can get in, but the energy that that system generates can get out. Right? So open, closed, and then isolated. An isolated system would be a system like this canister of oxygen, where you can't exchange matter or energy. And I used the example this morning, like that canister of oxygen. I remember before my wife passed away, my late wife, before she passed away, she was on oxygen. And after she passed away, there was a lot of the material still left. We had a oxygen generator and all this stuff and these little tanks. and I kept them in the garage. Thankfully, it was an isolated system, because if the system wasn't isolated, we talked about this thermal energy before on Friday. Imagine what happens when the temperature of the room goes up, the temperature of the system also goes up if it's not isolated. And so for an isolated system like this, that's dangerous, right? Because you get those oxygen molecules agitated, and you agitate them enough that could cause an explosion. So with an isolated system, it can't exchange matter or energy with the surroundings, right? It's totally isolated. Anything that happens within the system, and the surroundings don't affect it. All right. So when we think about ways to change the internal energy of a system, right? There are three ways you do that. You either add matter to the system, and that's only for open systems, right? Because a closed system, it only gives off energy, but it doesn't absorb matter or energy. You can add matter to the system, like a car engine. You could heat it or cool it, and increase the thermal energy, or decrease the thermal energy by heating it or cooling it. Or you can do work on the system, right? You do work on it, or you allow it to do work on the surroundings. If the system is doing the work, the energy is going to drop. If the surroundings are doing the work on the system, the energy is going to increase. Um, so if we say that we're doing work on the system, that's going to increase the system's energy. Right? If we say that um, the system is doing work, that's going to decrease its energy. Right? So let's look at some examples of that, and then we're going to move on to another concept dealing with work and energy and internal energy of a system. All right. So when we think about adding matter to a system, a car engine is a great example, because a car engine is an open system, and you can increase the internal energy by adding matter to it. In this case, the matter in the form of gasoline. The more gas you add, the more combustion reactions that can happen to keep the energy of the system constant, as well as uh, keeping the system moving, right? So anytime I have an open system, I can add more matter to it. And it's the same with the reaction. If you're doing a reaction and one of your reagents is limiting and it runs out, if it's an open system, you can add more. If you still got excess reagent left over, you can add more uh, of the limiting reactant and get the reaction to continue going, right? So with a car engine open system, I can add gas, and that's going to increase the system's energy. If I heat or cool it, right? If the system is here, and I transfer heat to the system, right? Thermal energy, and the heat that's given off is given to the system. Obviously, the system has to be at lower temperature than the body that's transferring the heat. But when that happens, the energy of that system is going to go up, right? So when I transfer energy into a system in the form of heat energy that's given off by the thermal energy, or the kinetic energy of a moving particle, then that's going to increase the energy of the system. By the same token, if my system is higher temperature and it's giving off energy in the form of heat, and transferring it to some set of particles, then that's going to lower the energy of the system, because as the temperature drops, so does the energy, right? Because as temperature is dropping, molecular motion is slowing down, and the energy is also decreasing. On the flip side, on the other side, you can see as the heat is being transferred, the temperature is going to go up, and the energy of the system is also going to go up, because whatever the system is, whatever matter is composed of, that matter is going to get more agitated as the temperature begins to increase. All right, that's the second way. The third way, you can allow the system to either do work on the surroundings or vice versa. And again, in this particular case, we're going to use the idea of a piston in an engine. So if I have a piston that's just pushing up or being pushed down, in this case, I'm adding pressure, and I'm using that pressure. I'm adding it here, right here. But in the case of the system doing work on the surroundings, the pressure is going this way, right? So as this is released, the energy of that system is going to decrease. Right? So when the system is doing work on the surroundings, the energy of the system goes down. When the surroundings do work on the system, the energy goes up, right? Because now the system, in this case of a piston pressing on gas, right? The gas from the combustion, a combustion reaction or some type of reaction that's given off of gas. Notice here, as I compress these particles, that's going to increase the energy of the particles, right? The more compressed they are, the more they're going to vibrate against each other, and their energy goes up. So when the work is done by the surroundings on the system, you get compression in this case, and energy increases. When that pressure is released, then the energy decreases and the system does work on the surroundings, right? So all of that ties into enthalpy and calorimetry, and how we use calorimetry to measure enthalpy. So there are some things that we have to think about up front. And everywhere you see a D, it should be a delta. I apologize in that, but I meant to fix that last night. But everywhere you see a D, is delta. All right. So the one assumption we make is that at constant volume, delta U, which is the change in internal energy of a system, is equal to Q, which is the heat, right? We talked about Q on Friday when we were doing heat capacity and specific heat capacity. So this is the internal energy of a system, and this is heat of the system, right? And so at constant volume, those two are equal. At constant pressure, we have to add in the work component, because the work is the system pressing down on, the surroundings pressing down on the system, right? Work is expansion work, either being compressed or expanding. And that is this value here. So negative P delta V, where delta V is the volume or the change in volume. That's the change in volume. And P is the pressure. All right, so now we have another expression, right? So delta U, or the change in the internal energy of the system, is Q minus P delta V. So that's another relationship. At constant pressure, that's what we think about. So what delta H, when we think about how this relates to delta H, which is here, which is the enthalpy, and enthalpy is a measure, again, of the heat that's either absorbed or released by the system. When we think about that, the work function, the enthalpy is going to compensate for that. So we could replace delta H with the internal energy, and we can do that. Well, we can replace it and have a different expression. So here, right, the enthalpy, or delta H, is the internal energy of the system plus the work function. And if we replace that, we can also see this, right? So it's the delta H is Q, wrong pen, sorry. Q minus the work function plus the work function. So you can see that the work functions are going to cancel out. So the bottom line is, for any given system, any reaction at constant pressure, delta H and Q are equal. And we know here that Q, we know what that is C times the mass times delta T. All right. So we know that we know now we could substitute Q in with these terms if we don't know Q, and we can calculate it, and that is the same as delta H, because remember, Q is always in joules. All right. So here, let's talk further about the enthalpy, which is, again, the heat either absorbed or released by a system. If heat leaves the system, then it's exothermic. And I'm going to show you that again with the curves. If heat is added to the system, then delta H is positive, and I'll show you why. All right, so we say that a system is, if delta H is there, and we say that the system absorbed energy, right? We can show that. So let me show you this on let me put this curve back here. We already know all the other terms, delta G double dagger, and we say this is A going to B. This is the reaction system that we're looking at. So this is exothermic. We already mentioned that up top. And for exothermic system, we say that delta H, or the enthalpy, is going to be negative. There's a reason for that. When we think about delta H is C times M times delta T, it's the delta T function that makes it negative, because if it releases energy, then that means that the initial temperature is going to be lower than or higher than the final temperature, right? Because delta T is T final minus T initial. So if this number is lower than this number because of heat being released, right, that you expect the temperature to go down if heat is released. And so if the final temperature is lower than the initial temperature, that's going to give you a negative number. So delta T is going to be negative. So that's why you see That's why you see in this case delta H being a negative number for exothermic reaction. If it releases energy, the final temperature is going to be less. And so with that being said, you have a negative delta T, which is going to give you a negative delta H. All right. There's another term we can define here, which is, I think we defined it up top to that delta G, which is the Gibbs free energy. And this is literally the difference in energy between the products and the reactant. So again, energy is going this way, increasing. So the way you calculate that Gibbs free energy is to take the product energy and subtract it from the reactant energy. Right, and you can see here, because the energy of B is less than A, so that's also going to be a negative number. So delta G for exothermic reaction is a negative number. So delta H is negative, so is delta G for any exothermic reaction. And right, so that's the gap between the products and the reactants. That's my Gibbs free energy. All right, so the flip side of this is the endothermic reaction. So let me add another page in here. And if it's endothermic, the curve is going to be flipped. All right, so that's time, energy. This is my transition state. I didn't mark that up here, but I will. This is A going to B. So for endothermic system, you have to add energy, right? So that means that delta H is positive, right? That's because, again, if delta H is C times M times delta T, T final is going to be larger than T initial. If you're adding heat to the system, the final temperature is going to be higher. So T final minus T initial, this is going to be, the T final is greater than T initial. That means you're going to get a positive number. So delta T is going to be positive. And that's why we get a positive delta H. Same thing with the gap between A and B, the Gibbs free energy. So that delta G is going to be products minus reactants again. Right, and since the energy of B is greater than the energy of A, we can see that over here, because energy is increasing this direction. So B is going to be greater than A. That means you're going to get a positive number for delta G. So it's the same ideas, but it's flipped when it's an endothermic reaction. Everything that is true for exothermic reaction is the opposite for the endothermic reaction, right? And so the way we tie all this stuff together is we can actually calculate delta H for a given reaction. We're going to do that two ways before we leave. First, we can look at one way to calculate it, which is here. And before we do that, are there any questions? I know I'm talking a lot and maybe talking a little fast. Are there any questions about anything? All right. So one way to calculate enthalpy is to just do a simple calculation between the delta H and the work function, right? So it says in a reaction at constant pressure. So that's telling us what we're thinking about. If it's at constant pressure, that means that, let's go back up to our relationship up here. At constant pressure, delta U is Q plus W, right? Or Q minus P delta V. So here, that's the relationship that we're working with, right? So it says at constant pressure, 50 kilojoules of heat left the system and 30 kilojoules of energy left the system as expansion work. So the 30 kilojoules is my P delta V, and the 50 kilojoules is my Q, right? And it says, what are the values of delta H and delta U? Well, we can figure out delta U without a problem. And we can figure out delta H without a problem because the heat that leaves the system is 50 kilojoules. So it lost 50 kilojoules of heat. And so we could say that delta H is that, because we could say that Q and delta H are the same. And then for delta U, we can calculate that. It is Q minus P delta V. And if we put in Q as negative 50 kilojoules, and we subtract that from the work function, which it gave us as expansion work of 30 kilojoules per mole. I'm sorry, 30 kilojoules. Then we get negative 80 kilojoules. Right, so that's a simple calculation as long as you know the relationship between delta U, delta H, and Q at constant pressure or constant temperature. There's another way that you'll see this expressed, and it is in the form of being asked to write a balanced, what's called a balanced thermochemical equation. All right. So let me put that in here. Right. So in writing a balanced thermochemical equation, first you have to write the balanced chemical equation and then figure out how much energy was either gained or lost. And you indicate that at the end of the equation by just giving the value for delta H. All right. So in this equation, let me write the equation. It is NaOH plus HCl giving me NaCl plus water. Right. And it says the questions that we're working on says that you have 0.05 moles of NaOH reacting with 0.05 moles of HCl. And that's going to give me 0.05 moles of NaCl, right? And what it says is also, so these are molar amounts, and then it says that 2.9 kilojoules of heat are produced. Right? So if it's telling us that 2.9 kilojoules of heat are produced, what that means is that if heat is produced or given off, that means that the reaction is exothermic. And that matters because if the heat produced is, or if the heat is produced and the reaction is exothermic, then that number, when we work with it, we have to make it negative. So 2.9 has to be negative for all of my calculations. Right? So the energy for the reaction of 0.05 moles of HCl is going to be calculated by we're going to say that negative 2.9 kilojoules per 0.05 moles, because those are the numbers we were given initially. I said that negative 2.9 kilojoules of heat was released, and it said that from the stoichiometry that 0.05 moles of HCl were used. So we can say here that this is the relationship between the heat and the molar amount, which is negative 2.9 divided by 0.05. Now we just need to solve for delta H for 1 mole, because that's the other part of the question. How much how much heat is released by 1 mole of HCl? And we can easily solve for that. If we know the molar amounts, we can take that energy value right there and we can solve it. So 1 mole of HCl times negative 2.9 kilojoules over 0.05 moles of HCl, right? So here you cancel those two the moles of HCl out and you get negative 58 kilojoules. That's the delta H for the reaction of 1 mole. And so to write the balanced thermochemical equation, you just write it like this: HCl plus NaOH goes to NaCl plus H2O. And then you put the enthalpy term here, delta H equals negative 56 kilojoules, right? So that's the balanced thermochemical equation, which includes the energy the energy transformation values, which is what delta H is. So you took HCl and NaOH, you reacted them together, you got 2 different compounds on the other side. So the energy of HCl and the energy of NaOH are different when they get converted into other compounds, right? So you convert it into NaCl and water. So that transformation of energy has to have a value. So that's what delta H is measuring. So this is the balanced thermochemical equation. All right. So we got to stop there. We're going to pick this up on Friday. Remember, I'm sorry, not Friday, Wednesday. On Thursday and Friday and Monday, we're out. So that's really like, that's a lot of instruction that we're going to miss. But